Welcome everyone. My name's Roger Dargaville. I'm the Deputy Director of the Monash Energy Institute. I'm also a Senior Lecturer in Renewable Energy in the Department of Civil Engineering at Monash University. It's my absolute pleasure to introduce our speaker, Professor Doug Macfarlane. But before I do that, I'd like to recognise that we are meeting on the traditional lands of the Kulin Nation. In my case, it's the Wurundjeri tribe. And I pay my respects to their elders past, present and emerging, and express a warm welcome to any of those who are joining us today. 13 years ago, when I started looking at the energy transition problem, it was technically infeasible, economically prohibitive. But in the past decade, the imperative to act has become so much more stark. Technology costs have dramatically decreased. And in the case of Australia, we, or at least some of us, are now no longer asking how to get to just 100% renewables, but how to exceed that target and start exporting renewable energy to our neighbours. Exporting renewables, however, presents a range of challenges, and there are a number of options for achieving this outcome, and Professor Macfarlane will speak to us today about one of those options. So a little bit about our speaker. So Professor Doug Macfarlane is the lead of the energy program in the 𝗗𝘗𝗲𝗍 Centre of Excellence for Electromaterials Science. He was a PhD graduate from Professor Austin Engel's group at Purdue University back in 1982. Professor Austin Engel still publishing today, one of Australia's greatest chemists. And after postdoctoral fellowships in both France and New Zealand, Doug took up an academic position here at Monash in 1983, and he was appointed Professor of Chemistry in 1995. He's a member of the Australian Academy of Sciences, the recipient of both the Australian Academy of Sciences David Craig Medal and the Victoria Prize for Science and Innovation. On an account I did on Google Scholar, he has over 800 publications and is approaching 60,000 citations. He's on the editorial boards of Australian Journal of Chemistry, Chemical Communications and Green Chemistry. He is, in short, very well qualified in his field. So with almost no further ado, I'll welcome Doug to make his presentation on Towards the Ammonia Economy. Doug's going to speak for about 30 minutes, and then we're going to have time for Q&A. So please use the Q&A function on Zoom to ask your questions. My colleague Nancy will invite you to unmute if you would like to ask your question verbally. If you prefer that we ask your question, please make a note when you ask your question. For your information, the webinar will be recorded and will be available later on the MEI website. Okay, Doug, you can correct me on any of that information in the intro. I hope I got that all right, but over to you. Thank you very much.
Thank you, Roger. That's all pretty much correct, I think. So yeah, thank you for the invitation to talk to you all tonight about something I think that we certainly believe is a very exciting development. Let me just start to share my screen here. Everybody seeing that then?
If you want to put it in presentation mode.
Yeah,
great.
Do that. There we go.
Great.
So it's blocking off my screen, but hopefully that's okay. So yes, I'd like to just introduce you all, and some of you may already know some of this story, but hopefully show you, even though people, some new information about this idea of an ammonia economy. And one of the things I'd also like to do is almost a further step, if you like, in this whole renewable energy space is talk as we go about how this, in fact, links to the older idea of the hydrogen economy. Because as I've given this talk maybe a dozen times or so over the space of only the last 12 months or so, culminating in the paper that's listed there in green called A Roadmap to the Ammonia Economy. I've had a number of questions from people who were quite surprised by all of this, and they said, so what's happened to hydrogen? Where has hydrogen gone in this picture? And the answer is, it's very much part of this picture. So we'll have a pit stop on hydrogen along the way here. These two ideas are very much linked. And then we'll probably come back and talk about the ammonia hydrogen economy. This is one big picture towards the end. Okay, so let me proceed. This started in our work with a goal, shall we say, an ambition to tackle this problem. which is very much a current problem for the world, which is that basically a lot of our food, especially in the Western world, is made with modern chemical fertilizers, which all come from the Haber-Bosch process, which I'll mention a few times along the way here, which is a process that takes nitrogen from the atmosphere, combines it with a source of hydrogen from natural gas, mostly from natural gas, and produces ammonia, which is used to make fertilizers like urea. And that process to grow our food essentially produces about 2% of global CO2 emissions from the gas that's used. So we have this awkward nexus between food and climate sustainability that needs to be solved by changing that process for fertilizer production into a renewable source of ammonia, which is the key here. But then as we and others around the world over the last, say, 5 years or so have looked at how to start to tackle this problem from a chemical point of view, we've realized that there's a much bigger picture here, which I'll get to quite quickly. In an Australian context, it becomes a little special for us, I feel, and let me try to explain why that is so. It starts with this picture, which is one of my favorites. This shows the total solar insolation, so total solar radiation, averaged over the whole year, well, number of years here, night and day, summer and winter, and the dark brown colors are nearly 300 watts per square meter of energy power raining down on different parts of the planet continuously. Because it's average, this is continuous, and you see these dark colors, and you then compare it to the purpley blue colors, which covers most of Europe, northern Europe, you might notice, and then ask the question, well, where on Earth would you think to put lots and lots and lots of solar cells to generate lots of energy for some purpose? And the answer is there really isn't anywhere quite like it, like Australia. And to put that in context, that little yellow square that you can just see on my map, that covered with ordinary commercial solar cells, and I've got the details on the bottom there, that square is about an area of about 250 kilometers by 250 kilometers. And with those solar cells could generate 25 petawatt hours per year. And if this was an undergraduate class, I would get the students to work out what that number actually represents in more everyday units and what it probably means in energy supply terms. But I'll cut to the chase here and tell you that that's the electricity supply of the whole world from that little yellow square. And to further put that in context, that land area is only about the combined land area of our 4 or 5 biggest cattle stations in Australia. So this is a serious proposition in terms of land use in Australia. Put that in a more familiar context. If anybody wants to go and look further into this sort of information, Bureau of Meteorology has this sort of map, similar information with different units here. And I've also put some on this map. You'll see it's the northern part of, northern western part of Australia that is really the hotspot in this regard. So this information is freely available. Question is, if we can generate lots and lots of energy, what do we do with it all? It's stranded is the expression we often use to describe this situation. We can generate it in places in the country and in the world which are far from our own markets and far from the markets, especially to the north of us. The question that arises is, how do we get this energy to market? And so these arrows sort of represent where it might go. I'll maybe just tantalize everybody with the question as to why that big arrow emanates from the South Island of New Zealand right now, but that's a topical point in New Zealand politics right now. The question really is, what's in that boat? What is that boat carrying this energy out of Australia? So the answer that's been emerging is there are several possibilities, but Japan has been one of the leading proponents, if you like, of some form of liquefied solar or other renewable energy as an import from Japanese point of view. And as you can see in this picture, this is the Japanese Minister for Economy, Trade and Industry and our Senator Birmingham visiting us in the labs earlier on this year. And very much Japan has prompted the rest of the world to start thinking very hard about how to do all of this. And the overall picture that we've developed, we refer to liquid sunshine. In other words, we know where we're going to get the energy from. It doesn't have to be all solar, of course. It can be a lot of wind and hydro. The question is how to put it into a liquid form that you can put into a bulk carrier. So you can see our little graphic there showing some form of transformation in the petrol Bowser wand, so to speak, filling up the ships. The first approach we call Gen 1, which is very much topical today, and there's a lot of buzz about hydrogen, to export green hydrogen. It needs to be liquefied. And while that's definitely an emerging technology, the problem of liquefaction of hydrogen, it's an expensive technology. It's in large scale, it's a largely untried technology, and it's somewhat expensive in energy terms as well, in the sense that there's a fraction of the energy that's consumed purely in generating liquid at very low temperatures. But nonetheless, let's talk a bit further about that and the second generation I just mentioned. I'll refer frequently to some of these color schemes, and in case anybody is wondering about what is green versus blue and so on, green is the phrase we use to describe a material that's made from renewables, the energy source of renewables. There's a talk about blue hydrogen, and blue ammonia, which in fact is effectively the traditional sort of hydrogen or ammonia, but with carbon capture and storage added to it. So that's blue, and our exports for the moment are likely to be mostly blue hydrogen and ammonia, but going green hopefully in the near future. And you might also come across purple, which refers to nuclear. So let's just mention hydrogen at the moment. Just the process of making green hydrogen by electrolysis is one that is common to much of what I'll talk about, as in the methodology of electrolysis is common to both hydrogen and ammonia. So I'll just introduce what that is in hopefully a somewhat familiar form with these pictures. So we have a cell into which we're applying current with some electrodes, and in the video to the right, it's just some copper wires, and that's salty water that it's sitting in. And then in that particular picture, we're making hydrogen at one electrode and oxygen at the other electrode. And modern day electrolysis for hydrogen is really just a scaled up version of that simple process. That's an application or an area of energy chemistry that we're very busy within our group in Monash Chemistry, led by future fellow Sasha Simonov, a partner of mine in much of our work. And I won't go through all this slide, but just to say that there's a lot still to be done in this electrolysis process to make hydrogen. And then what we're going to do with the hydrogen is the question that emerges from that. And there's a number of projects here working with local companies such as ANT and Woodside, and we have support from the likes of ARENA and the ARC in doing all of this. And I'll just pick up on one particular recent bit of deep chemistry, so to speak, some novel chemistry that came out of some things we were doing, which illustrates how water electrolysis to make hydrogen is still an emerging, lots of science to still be done here. The traditional form of water electrolysis is usually done under alkaline conditions, so simply caustic conditions, where the oxygen evolving electrode, the anode of the process, is most facile, most productive, but the hydrogen producing electrode, the other electrode, that's not its favorite conditions. But that's the state of the art today. It's very desirable to switch those to acid conditions, more like a lead acid battery than caustic conditions. But the problem is that the catalysts just aren't stable. And here's a bit of work that we, in which we developed a mixed metal oxide catalyst for the oxygen evolving side of the cell, which is very stable under these acidic conditions by a very clever self-healing mechanism. The catalyst is constantly healing any tendency for it to corrode under these strong acidic conditions. So we see a strong future for acid-based electrolysis for hydrogen. So if we then start to think more and more about how we're going to move this hydrogen around, one of the concepts that has emerged is to use ammonia. So ammonia, current day ammonia production takes hydrogen from methane. We're going to make it green hydrogen, but makes ammonia in this thing called the Haber-Bosch process. So that's a big, large-scale chemical engineering process. We'll just call it HB in this slide. That's for fertilizer production. But if you begin to grow the concept of it, you can imagine using this as an energy carrier for other applications of the energy. So generation 2 of our liquid sunshine, exportable sunshine, is ammonia generated from the hydrogen that we've just been talking about, and Haber-Bosch plants. And here's a little bit more about how this would work. So if we have our stranded renewables at the top, we have this very simple schematic of an electrolysis cell that I've drawn here. This one is showing alkaline conditions to make our oxygen and our hydrogen. We put it into this little blue box we call Haber-Bosch, which is in fact that massive chemical engineering plant that I showed before, the biggest of which in Australia is in the 𝗗𝘁𝗲. It takes in nitrogen, it takes in hydrogen, and it produces our ammonia. One of the interesting things about ammonia, the reason that it's appealing in this situation, that it can be made into a liquid at room temperature at around about 12 atmospheres of pressure. And it has a reasonably high energy density in that liquid state. What can you do with ammonia is the question. Well, the first answer to that, the one that sort of emerged in particular from CSIRO 3 or 4 years ago, is that you can crack the ammonia. This is once it's landed in Japan. It could be in the fill station. It could even be on board a vehicle, this cracker. To produce hydrogen, the nitrogen that we started with is regenerated, so that's a circular process. And the hydrogen then can be used in a traditional fuel cell. So that gets our energy from renewable through hydrogen, through ammonia, and back to energy again. More recently, there's been a wide realization of just what you can do with ammonia directly. So without cracking it back into hydrogen, we can use ammonia directly as a fuel. It is in its gaseous form. It is in many ways similar to methane, CNG, as a fuel. And this picture shows a direct ammonia-fueled engine that's being developed for marine use, as in for shipping. And that's a very important application of ammonia. There's almost no other solution to the renewable shipping challenge that's emerging rapidly in the last year or two, other than ammonia. Japan's been very much a leader in this. So here's a power plant, electricity generating plant, prototype scale, being built to run on ammonia. Ammonia as a fuel. There's no hydrogen involved at this point. This is directly as a fuel. And if you look at the date on that picture, that's already a couple of years ago. It's also possible to co-fire traditional gas and even coal-fired power generators with a fraction of ammonia in the fuel mix. So a coal-fired solution where you transition from a pure fossil fuel to at least partly to a renewable fuel is very much possible with ammonia. Once you sort of recognize that possibility of running engines and other similar applications of using ammonia directly as a fuel, the idea of the ammonia economy then emerges. And this picture is sort of designed to summarize all of the things. It looks a little primary schoolish, but in fact, everything that's on this picture is very much possible with ammonia. You see the agricultural application, traditional one at the top, of course. Ammonia is very easy to store and to ship, as we've just been talking about. We've been talking about how we can use it in engines of various sorts, and most importantly, shipping. We'll come back to that. Trains and buses, of course. Buses running on ammonia were used in Belgium in the Second World War. Somewhat less obvious, but in fact very possible that you can run a traditional turbofan jet engine on ammonia at the temperatures involved. It burns very much like the fuel vapor that's traditionally used, even aerospace. So the point is that that the ammonia cycle then. Ammonia going through and nitrogen coming back to the original point of production of the ammonia by electrolysis becomes very much a concept in its own right. So this is all summarized in this article that we published in Joule a few months ago, called A Roadmap to the Ammonia Economy, and that is, I believe, freely accessible, and I can certainly supply a version to anybody who would like to read it. And in fact, most of this talk is very much a summary of what's in that paper. So all of that thinking about how to use ammonia then reached back in that picture to, well, how to actually make the ammonia, and the question is, can we avoid this Haber-Bosch process, which is large-scale chemical engineering, a very significant plant cost, and can we do the ammonia production directly in the cell that was previously making hydrogen? Can we tweak that electrolysis cell to make ammonia? It's a very similar process to making hydrogen. And we call this Gen 3. So ammonia by direct nitrogen reduction. So let me talk about that for a little while here. So back to this picture, and what I've done is, compared to the previous picture, we've removed the Haber-Bosch process. We're bringing nitrogen directly into the cell to get our ammonia, and the rest of the picture is the same. And the overall reaction then has switched from producing hydrogen to producing ammonia. So this is the question about Gen 3 as an energy source for ammonia. And a little bit more detail on how that would work. So to be clear about all the things that are going in and coming out here, so we have that electrolyzer, which is now tweaked, so to speak, to produce ammonia. It takes in nitrogen from the air. And how do we get that from air? We have a device called an air separation unit, which by one or two or three different means separates the nitrogen, which is roughly 80% of air around us, separates that out and leaves aside the oxygen, which we don't want, although it's not a hugely massive problem, the oxygen, but it just lowers our efficiency. We need water, of course. And the result then is this ammonia, which we can liquefy and store very easily. This is the Gen 3 concept. But there is, as we dig down into this, there's a little bit of a problem here, which is that it's actually quite a challenge to make ammonia. The thermodynamics of it don't look too difficult, but don't look too difficult in the sense that the energies involved aren't seriously bad. In fact, ammonia should be able to be produced at a more benign potential than it takes to make hydrogen. The problem is that hydrogen is very hard to avoid. And the reason for that is that nitrogen has a very low solubility in almost all solvents, especially water. So anything we might want to do this electrochemistry in, this electrolysis in, nitrogen just doesn't want to be there. And that then becomes a very big challenge to the electrochemical design of the cell. And if we don't get it right, we end up just making a lot of hydrogen. And this isn't a very good way to make hydrogen. So in this endeavor then for Gen 3, the pathway has split up into several different pathways. The one that I've been sort of hinting at there is at the bottom, which we call aqueous direct electrocatalytic production of ammonia. So nitrogen to ammonia on this electrode in an aqueous solution. I won't go into the other ones, other than I'll just mention that there's an alternative, which is the continuous mediated one. I'm going to talk a bit more about that in a moment. And when we analyze these four different approaches with this traffic lights approach, what we find is that none of them is perfect, not at all. Whether it's selectivity, in other words, does it produce mostly ammonia or does it produce something else, mostly hydrogen? Does it use a lot of energy? And does it do it at a sufficiently impressive rate to be practical? So we rate that according to traffic lights. The first thing we run into is a whole lot of problems around the aqueous one. Now, there's been a lot of work here, but in the end, some of it's very doubtful. And a paper that is literally being accepted as we speak. In this paper, we've analysed as an avalanche of literature on this aqueous nitrogen reduction reaction to ammonia. And according to our traffic light analysis here, it's the same colour scheme. Almost none of it is, what should we say, a genuine positive result, a reliably positive result. And I'm afraid to say that this is only one page. This particular analysis goes on for something like about 6 pages and some 100-odd references, most of which are absolutely unreliable in the sense that we believe that there's false positives. So there's some really big problems here. And again, that will be free to get hold of in Nature.com very soon, that article. The problem is that it's very easy in the laboratory to either find ammonia from other sources or to make it from just about anything that's got nitrogen in it. Will make ammonia more easily than nitrogen, the gas, because nitrogen, the gas, N2, is extremely stable molecule that's very hard to break up. Everything else is much easier. So purification of everything and very, very, very careful control experiments, including working with isotopic nitrogen, is absolutely vital. And without doing that, a result is usually unreliably positive. However, there is on that pathway slide that I had a moment ago, there was this mediated approach, which is a different approach to doing this, which involves an intermediate, effectively. And in the slide I'm showing here, this intermediate is lithium and lithium nitride. The process doesn't directly produce ammonia, it produces this intermediate compound, lithium nitride, which, when in the presence of some H from some other source, like water or like hydrogen, will then produce our ammonia, which is released here in this cyclic process. So this is a different kind of reaction, and is not such a new reaction. It's been a well-known one for many years, and is therefore much more reliably proven to be producing ammonia genuinely, and it does so at much higher rates, and that's why it's a very appealing one. So then, just to mention some of our own work on this. Here's some results from our labs in recent times. We're exploring this mediated approach. We use pressure as a variable. The yield rates here, I'll explain that, give these yield rates some context in a moment. But more importantly, probably, is to notice this efficiency. This thing we call Faraday efficiency is also a measure of selectivity. So we were looking for 100% selectivity, and if it's not sort of somewhere in the upwards of 100%, then the reaction is actually doing something else with the electrons that are going into it. So high Faraday efficiency is important, and you can see here that we're getting upwards of 80% and even above 90% at times. The cell that does this can run for these experiments run for over a day continuously, and we can get sort of fairly continuous 80% Faraday efficiency and so on. And from an experiment like this, where we now totally measure the amount of energy that goes in by electrical energy means, we can then begin to calculate genuine energy efficiency in this, which is this particular experiment is about 24%. Not highly impressive as it stands. This needs to get better, but it's possibly one of the first times that we've actually been able to get a true energy measure in this process. To just to continue talking about that kind of approach, there is a strong role here for our artificial intelligence, machine learning type of people to be able to do calculations of the detailed mechanisms that are in play here. We've got a nitrogen molecule, this blue dumbbell thing, which needs to somehow or other get split in half. And this is the difficult step usually, by the metal reaction, the metal surface that it's reacting on. And the people who are able to do calculations around this, these are bond lengths in angstroms of how the molecule, see how this molecule decides to sit vertically. So one nitrogen becomes different from the other in the first step, and then we get progressive steps of reaction as we go through. And we can see how this goes in terms of an energy profile as well. Very, very useful addition to our understanding of how these reactions work. To go back to some context for those numbers I showed before, this is a slide that hopefully does that. We've got some literature and other policy type targets for this kind of process. One is from 𝗻𝗲𝗿𝗲 and colleagues at CSIRO from a few years ago. They suggested that in this particular number scale, that around about 6 on this or 6D on this scale is about necessary for this to be considered a practical result. The US DOE suggested that a true target would be more like 600 on this scale with 90% efficiency. This is the Faraday efficiency number here. Here's some other literature data, and here's where we are in this project, which is funded by ARENA. I should have mentioned that already at this point in time. And this green bar of where we're at has moved quite substantially even in the last few months. So we now have this target, which is also the DOE target, very firmly in sight, using things like very carefully designed electrode structures. So our current electrodes is simply a piece of copper, a flat piece of copper or a copper wire. Structures like copper foam or this kind of printed structure, which is something that can come from our colleagues at the University of Wollongong, can be then a way of increasing the yield per unit area of the cell, which is what that particular metric is all about. And then using that kind of approach, we're hoping to scale up to eventually in the near future to a device which we call, it should be about somewhere between this thing that looks like an iPhone and a small fridge would be the way to think about what this device is going to look like, and that could consume of the order of 1 kilowatt of power. So that will be the subject of a spin-out company that we're planning to form, hopefully before the end of the year, called Jupiter Ionics, to pick up the various IP that we developed in this field and take it to higher degrees of development. Coming back to the roadmap, it's useful to note that ammonia is already competitive as a fuel with other common liquid fuels. So we can ignore most of what's in this table. It's just a bit of extra information here for a bit of detail for anybody who wants to delve into it. But the last couple of columns are the interesting ones. But by the time we get to, if we compare the cost of a fuel, and we picked up a number of different fuels in different countries just to be illustrative, but there's lots of information that you can delve into to find other information for other countries. But for example, if we look at the price of diesel in the US, about $1 a kilo, and then convert it, and this is the important point, is this last column, convert it into dollars per kilowatt hour of energy, which in the end is the ultimate thing that you're buying is energy. So diesel works out in the US at about 0.083 or 8.3 cents per kilowatt hour of energy. Ammonia is cheaper than that. If we look at the price of LPG in Germany, it's also about $1 per kilo. That works out to be for LPG to be about 8 cents, which again is more expensive than ammonia is today. These are current day prices. Petrol in Japan. Japan's a fairly expensive country to buy petrol, so that is substantially more expensive per kilowatt hour. And a very important one for the future is bunker fuel, the fuel that is used for large-scale shipping. It's often called bunker fuel, and it's a heavy oil, typically about 5.5 cents per kilowatt hour, which is about the same as ammonia. And that point has now attracted the attention of the shipping industry, who are seriously considering ammonia and ammonia-designed engines for the future of shipping. And ammonia-powered ships are already on the drawing board in a number of countries. So with that in mind, we speculated in our paper about how this might all unfold. We were tempted to use a true timescale at the bottom here, but we knew we couldn't really be sure about what the timescale might be. So we used commercial readiness index numbers instead for these different generations that I've talked about and how this would unfold. Note the log scale on the left-hand side for this. And because this is log scale, we can show global fuel consumption on the same graph as current day ammonia production. Also, a useful line here is the shipping fuel use today, and this is in energy terms, petawatt hours per year. So shipping is about 35 petawatt hours per year today. You can see it's a fraction of global fuel consumption. It's a fair bit more than total ammonia production, but ammonia one day could become, way over here somewhere, the source of most shipping fuels, and that's a distinct possibility in designers' minds at the moment. So we see this unfolding then in various generations. Gen 1 will of course take over from current day, effectively black ammonia. Gen 2, which uses the green hydrogen, will take over as plants are converted to green hydrogen, and green hydrogen becomes more readily available, and new plant is built. So that's as this starts to build up here. And then we think that Gen 3 is the ultimately deployable form because it doesn't require the massive scale of the Haber-Bosch plant anymore and can be built at very small scale all the way up to very large scale. Just to finish off with, I think it's important to note, and we did this in the papers, there's a lot more detail. I won't try to describe all the slides. This is a seminar in its own right, but I think it's important to note or to make sure that as responsible scientists and engineers and technologists, that we don't effectively fix one problem that the world's created for itself revolving around carbon dioxide production. By transitioning to a fuel based on nitrogen that creates another problem to do with nitrogen and the nitrogen cycle. So this is the global nitrogen cycle that's summarized in this slide. We didn't draw this. This is taken from an important paper by Fowler et al. But basically what this says is that this is all of the natural processes are added to by the Haber-Bosch process and large-scale agricultural biological nitrogen fixation, BNF. And what you learn from this is that total conversion of nitrogen from the atmosphere to other forms of nitrogen, including ammonia and all the other things that ammonia is used to produce, is about 413 teragrams per year. And about half of that is due to anthropogenic activity. That's mostly these three things over on the left. Okay, it's about half of that. So this process of turning nitrogen in the atmosphere into useful chemicals and food is only about 100 years old. The Haber-Bosch process is only about 100 years old this year. So the other point then is that only about 250 to 350 of the 413 is clearly returned to the atmosphere or deposited. So it's important to think about where the rest goes. So we have a problem here in understanding the total cycle, and we need to understand this. Only about 17% of that anthropogenic nitrogen is actually consumed by us as food. The rest is in various ways wasted. And a lot of that ends up in the ocean. So through us or just through runoff from fields and other forms of environmental change into river systems, into the ocean, and then the marine processing load of processing nitrogen compounds is about doubled due to anthropogenic activity in the last 100 years. Problem with that is that N2O, which is a particularly serious greenhouse gas, has a lifetime in the oceans of hundreds of years. So we're only in the midst of understanding what's going on there. And nitrates accumulating in the ocean, part of that cycle, are beginning to change the ecosystem of the oceans. So we have to be careful to understand all these things, is my point, before we allow this to go to massive scale. Or to put that another way, we've got to be very careful about how all this nitrogen is ultimately recycled back into the atmosphere. So with that, I'll just finish with reminding us, if you like, that a lot of things that I've said aren't trying to kind of elbow hydrogen out of this picture. Hydrogen is very much about the same goals. There will be clearly parts of this, and it could be, for example, in vehicles. Ultimately, there's a fleet of vehicles building up in various countries, especially Japan, that are hydrogen fuel cell cars. So hydrogen is a demanded commodity, and ammonia is simply the way to supply that hydrogen to the vehicle, and the cracker maybe in the Bowser, so to speak. So hydrogen certainly has a role to play here, and ammonia is one of the ways that that hydrogen can be moved around to point of use. But in other applications, such as shipping, it's much more obvious to use the ammonia directly. So therefore, we've begun to just talk about this as the ammonia hydrogen economy. These are not different ideas, they are one and the same, and they both support each other, so to speak, in finding the right niche applications. So with that said, I'll simply finish with this, and that's the guys back in the lab. They are back in the lab at the moment, fortunately, and of course our funding agencies, in particular ARENA. It's very pleasing to see ARENA has been refunded for some time to come, and the Australian Research Council through our Centre of Excellence, who are the original source of much of our funding for this work. So thank you for your participation in this webinar, and I'm very, very happy to further discuss and answer any questions you might have.
Right. Thank you very much, Doug. I'll applaud on everyone's behalf.
Okay.
I'm sure there's rapturous applause out there in the virtual world. I always find with these webinars, when you're sitting listening on your own and you have no idea how many people are out there, it feels a bit odd. So I like to let everyone know there's 100 people in the room listening to this talk, and I was watching the numbers every once in a while, and I noticed that we stayed pretty close to that 100 level the whole way through. So congratulations to everyone for maintaining their concentration and their ability to stick with Doug's presentation. I'm sure you're rewarded for sticking to the end. Okay, so I'll start off with one question for you, Doug. And while I'm asking that, I ask everyone in the audience to please enter your questions into the Q&A. We've got one question, one rhetoric question from Oliver Yates. I don't know, Oliver, you actually want to ask that question. We might invite you to unmute your microphone in a moment if you'd like to. And then the second one is from David Prins, who is asking to come back to something you mentioned at the start of your talk. But again, David, we'll ask you to ask your question in a moment. While Nancy's sorting that out, Doug, one thing you didn't mention during your talk is the issue around safety with ammonia. Mm-hmm. And ammonia used to be commonly used as a refrigerant, and but one of the reasons why people didn't have ammonia-based refrigeration units in their homes was because ammonia is a pretty dangerous substance. So can you comment on how safe it is, or what measures need to be taken to make sure it is safe?
Look, absolutely. There is a lot of discussion going on about this, and we do cover this in our roadmap article if people want to look into that in a bit more detail. And the purpose of the article, by the way, is to very much provide what we hope are useful references to all of these sorts of questions. So it's a constant theme throughout all of the application section of the article of making sure that we cover off on NOx emissions. That's the whole issue of effectively environmental impact of what we're talking about here, and also of safety. So both of those things are constantly mentioned there. The point about refrigeration, Roger, is an important one. That the use of ammonia beyond the fertilizer industry, where it's transformed mostly fairly immediately into products like ammonium nitrate. And we're all aware of what's happened recently in Beirut, of course, with ammonium nitrate and then urea. But it's also been used in the refrigeration industry, and still is in large scale commercial refrigeration. The point is that there is actually quite a lot known about ammonia, safety handling, and so on. One of the good things about it is, in fact, that our ability to smell ammonia far exceeds any kind of toxicity, the toxicity level for ammonia. We can smell it long before it's toxic. So it's an annoyingly smelly gas, yes, but when you can smell it, it is a long way from being toxic yet, and that's a good thing. There's been some comparative studies looking for incidents, to compare incidents where there's been an ammonia accident compared to something similar that's happened with a hydrocarbon fuel like LPG. And there was an incident, case in point, in the US, where a small train tanker had derailed and split open, and so a cloud of ammonia then swept through a township somewhere in the US, and a similar event where a train tanker of LPG had derailed and split open. The latter caused an intense fire and killed a number of people. The ammonia didn't. The injuries from the ammonia were not nearly as severe. So the outcome of that sort of comparative analysis showed that, in fact, ammonia may be in fact less dangerous than what we're all used to, and this would be true also for an aircraft carrying large amounts of ammonia or shipping. So it's potentially less dangerous in that kind of respect than hydrocarbon fuels are. I'm talking about the flammability or the explosion risk there.
Okay, great. Thanks, Doug. So feeling much more safe about ammonia now. Thank you. Okay, so we've got a couple of questions now. Hopefully, Nancy, you've been able to get Oliver. And I think your question's rhetorical, Oliver, but I think it's also worth mentioning anyway. So hopefully you've got the...
Yep.
Great, thank you. Yes.
Yeah. Look, the question was: as the minister, obviously in the roadmap, seems to have many times presented the production of ammonia is only really possible through gas, right? Through more gas. Obviously, you've demonstrated quite succinctly how you can make it with renewables in the hydrogen chain. I'm just wondering whether you feel that the research that you're doing is finding its way to other relevant ministers in a way that they fully understand how renewables can be used to meet the nation's fertiliser and ammonia needs.
Look, I think we're making some headway, but whether we could accelerate that, look, there's lots we could discuss about that. I mean, the visit that we had that involved Senator Birmingham, I think certainly my impression was it was an eye opener for him. We've also had Senator Van visit recently and was equally, I think, impressed. And the paper itself has gone to a number of desks in Canberra, and including, of course, Alan Finkel's. He's very much aware of ammonia and all that it can do. So the message is getting there. The Minister for Energy is an interesting challenge, shall we say? But absolutely, I think we should adopt every means that we can to get this message across.
Great. Thanks, Oliver, and thanks, Doug. Okay, David Prinz. Nancy, can we unmute?
I can see the question on the.
See the question. So it's just nice if people can actually ask it. It adds a nice
sure, yeah,
touch. Yeah. So thanks, David. I think you should be good to go now.
Yeah, thank you very much, and thanks for that presentation, very informative. Mine was a straightforward question that you'd mentioned earlier. There was, on the stranded energy map, there was this big arrow coming from New Zealand, South Island.
Yep. This is very interesting from a number of points of view. So, as you're probably aware, New Zealand put in enormous resources in hydro in the South Island of New Zealand, Lake Manapuri in particular, largely to feed the Bluff aluminium smelter, which Rio Tinto has recently walked away from. That's a month or two old, that news. And this is a very, very, and hydro, by the way, is the most perfect approach to any of these green fuel production methodologies, because it can give you continuous power. So this could bring up a discussion about intermittency. So these technologies can deal with intermittency quite well, actually. So having a cell, whether it's making hydrogen or making ammonia, sitting, varying current up and down, or power up and down according to supply, is certainly possible. But of course, lowers the capacity factor of the kit, so to speak. So it raises the question about capacity factors. But hydro is continuous, potentially continuous, and New Zealand seems to now have a very large resource of hydro, looking for a role to play. And New Zealand is rather interested, I think, in what it could do with that hydro.
Would the geothermal in New Zealand also contribute to that, or it's much smaller?
I think it's much smaller, but it's certainly a possibility. And I've also sort of had some discussions with the Minister for Energy in NZ some year or so ago. There's quite a lot of interest in what you might call microscale generation of whether it's geothermal or just small-scale hydro into some form. And ammonia seems like a very appealing form. They've got a concept of a truck going around, like the milk truck currently goes around at the moment, collecting ammonia.
Right. Okay. Thanks very much, David, for those questions. Okay. So, Nancy, can we have Adam Cermiak next to please ask his? He's got two questions. How are we going for time? We've got a bit of time. So, Adam, you can ask both your questions. Why don't you ask both of them, and then Doug can respond.
Okay. Thank you so much, Professor. It's a pleasure. My name is Adam Cermiak, and I'm the last year PhD student in Professor Udo Bach group.
Mm-hmm.
First question, how exactly do you combust ammonia? Like, what do you do? Especially, in that power plant in China, do you burn it in some sort of traditional way, like in the diesel engine, you increase the pressure, or is there any other process? And what's the potential outcome? Because I know it's, there is a nitrogen, so probably we're talking about the nitrogen oxides or...
Yeah. Again, there's quite a lot to discuss there. So it burns. So for anybody who's not sort of into combustion engineering, let me explain that. Of course, once it's released to 1 atmosphere pressure, it's a gas. So at this point, it is entering the combustion chamber or the engine, much like the vaporized fuel does, or even just natural gas does. Now, it doesn't burn it doesn't ignite as easily as the hydrocarbon fuels do. So that needs some engine modification, or in some cases, there's either a starter fuel that gets the engine going and everything hot, which obviously helps the combustion initiation, or it's what was I going to say? Just modified. To take account of this. So there are a number of people producing a variety of different ammonia engines that have got these modifications in them, including a colleague at RMIT who's working on a small scale generator type _2 or 3 kilowatt type device that is running on ammonia. A little hard to start, he says, but once he gets it running, it works fine. Okay. Now the NOx equation is an important one, right? So you're burning ammonia in oxygen. Unless you can get the stoichiometry completely correct, you'll get some NOx's, and it's almost impossible to avoid them. However, it's relatively a very well-known technology already to use ammonia, a small supply of ammonia injected into an exhaust stream from an engine. This is already true in Europe with diesel engines in vehicles, or even in power stations, to use ammonia because it reacts with NOx very readily to produce nitrogen, dinitrogen. So the technology of dealing with the NOx in exhaust streams is actually already in existence and well understood. So however this works out, there's a second stage, if you like, processing that can be applied to deal with the NOx. And the challenge is probably just making sure that the NOx is monitored continuously in that exhaust stream, so that the ammonia is injected into that exhaust stream at just the right stoichiometric amount.
Okay, thank you so much. The second question is, because we've got at least a couple Asian countries around Australia, and why can't we just sell them liquid nitrogen, liquid hydrogen? Why don't we just lay gas pipelines, just exactly like, the famous one, the Yamal from Russia to Europe, or the Nord Stream, which goes underwater? The distance between Kagoshima in Japan and Darwin is only 4,600 kilometers. Mm-hmm. Whereas in 1993, the Yamal gas pipeline was laid from Russia, and it was 4,300. So it's almost the same distance, but we've got at least 30 years difference, like in our technology. And also we are like one of the largest producers of the iron ore in the world. So why can't we just make huge pipeline and we're just going to transport all the hydrogen to the surrounding countries?
Or equally, probably more effectively, actually, ammonia. So everything you said about natural gas pipelines, there's some quite substantial networks of ammonia pipelines around the world as well. So I should have mentioned that the pipelining is well known. Large scale pipelining of hydrogen is not so well known. And there are quite a number of materials issues in regard to all of that. So I think that, but I'm not the expert to ask on this point, but I think if people came to the idea of laying large-scale pipelines, and we don't need to go to Japan necessarily. I mean, Indonesia is an immediate market for a lot of this energy, very close to where it could be generated. Then the ammonia might be the preferred thing to put into that pipeline.
Okay, thank you.
Okay, so Nancy, can we now unmute Prakash Aryal? And I see Ariel Liebman has also written a question. Hi, Ariel. Ariel's the director of the Energy Institute. But Prakash's question is quite similar. And so in the interest of giving other people who we don't hear from often the option of speaking, we'll let Prakash ask the question about economics.
Thanks, Roger. Thanks, Professor Doug. So my question is like you mentioned certain yield target according to the log scale timeline that is like 60 or 600 gram per meter square per hour. That is maybe in terms of efficiency, technicality. But we have such similar target in terms of cost of ammonia production or cost of such a hydrogen production. I heard somewhere else like target price of hydrogen from renewable means is equivalent to $2 per kg that is set somewhere else. So is there similar thing for ammonia as well? That is Gen 1, Gen 2, Gen 3 you mentioned? Or yeah.
I don't think that it's been quite expressed that way because a kilogram of hydrogen is this is all to do with the molar masses of the compounds and their relative heating values is the equation. So you could convert that number into the equivalent for ammonia. That's just a little bit of chemical arithmetic, the $2 per kilogram. So I think, sorry, go on. Oh, somebody was saying something there. So you could do that calculation. It's not commonly sort of thrown around, so to speak. It's usually at the moment expressed either in the metrics that I talked about, or in a gallon of gas equivalent, the GGE number that the DOE in the US loves. And what they're saying is, well, and this is the same principle as I used in that table, which is by the time you convert it to and even use it in an engine. So this allows for the engine efficiency to come into the equation. That's useful to bring into it. So what does it cost for the gallon of gas equivalent in terms of how far you can drive a car or how far you can drive the bus? And that's a relevant thing to do. So that number is commonly bandied around, and I think once again it's about $2 or $3 per gallon of gas equivalent, I think, for any fuel.
Thanks.
Okay, thanks for the question. Okay, we're almost up to the hour, so in fact my clock's just ticked over. So we'll finish up with one last question, Doug, and this one's from Tim Jordan. Sorry, I just scrolled off my screen. There we go. Tim's asked me to read the question out for you. So he writes, France, Germany and the UK have recently pledged massive support for hydrogen, billions of euros over the next decade. Is Europe on the right track? And I guess he's maybe asking one of two things. Is that the right amount of money, or is hydrogen the right choice of
fuel? This is so the answer is probably yes on both counts. Although I think we could always use more money, couldn't we, in this endeavor, this important endeavor? Most of these European countries are well understanding now the role that ammonia plays in this. So when, for example, the UK talks about hydrogen, ammonia is very much also in there in this picture. The Royal Society in the UK produced a sort of scoping document, which was published in about February of this year. So that's well worth looking at, and it sort of covers the same perspective on ammonia as we did in our roadmap article, and this is very much sort of focused on what this could mean. This is ammonia I'm talking about now in the UK, and we've had quite a lot of interactions with groups from Germany, and they equally were very clear on ammonia as being potentially the part of this picture. Right, and well, one of the things that it clearly represents for countries that have a lot of excess wind, so they don't have what you might call the export-import problem necessarily. I think the UK, for example, and maybe even Germany have got the potential to be almost energy neutral, energy independent. It's the storage problem. And hydrogen in very, very large quantities, of course, is difficult to store, much, much more so than ammonia. So whether ammonia is just seen as a way of storing hydrogen is a question, but it's certainly part of the picture in most of those countries.
Okay, great. Thanks very much, Doug, for tackling all those questions. Thank you, all the people who have typed in questions, and thanks to everyone who has attended the seminar. I'd like to especially thank 𝗫𝗫cy for all her work with putting this together, managing all the logistics. So I think we'll leave it there. Thanks, everyone. Thank you, Doug. Have a great evening.
Thank you.